Hello students, we are meeting again for our second lecture of industrial chemistry, and in the last lecture we have started with manufacture of basic chemicals. Under that, the first basic chemical that we are going to discuss is ammonia, and for ammonia we have discussed the principle behind manufacture of ammonia, that ammonia is prepared from nitrogen and hydrogen, which has to be taken in 1:3 volume ratio under pressure. Then only this reaction takes place, and depending on the source of raw material, that is nitrogen and hydrogen, it is it is classified, uh, or it is carried out by two different ways, and these two different processes are named as Haber's process, and second is modified Haber's process. In modified Bosch Haber process, the yield is 19%. So here we are going to discuss the actual manufacture of ammonia by modified Bosch Haber process. And here, the raw material, as I told you, nitrogen and hydrogen. The hydrogen is produced from steam, by use at temperature 1000 to 1400 from coke. On treatment with steam produces water gas, which is a mixture of carbon monoxide and hydrogen. The reaction is exothermic, so lot of energy is the reaction is endothermic, because 162.8 kilojoule energy, then sign is minus, so it is an endothermic reaction. And nitrogen is produced at the same temperature by treating coke with air, where it is coke is converted to carbon monoxide and nitrogen gas. This mixture is called as producer gas. This reaction is exothermic reaction. Now, because here one reaction is exothermic, one endothermic, so it is as far as energy audit is concerned, it is matched. And we are going to discuss actually how ammonia is produced by modified Bosch Haber process. And for this process, the flow sheet is like this. In here you can see air and coke are two different uh, sources, raw material, which produces air and coke mixture produces producer gas, whereas steam and coke produces water gas, as discussed in our last slide. Here, the output of both the uh, processes is given to oxidation tower. Now in this oxidation tower, the name itself indicate the oxidation will take place, wherein both the gases are forwarded to oxidation tower under pressure, and you can see here the steam is also introduced. Now what happens actually in oxidation tower? So in this oxidation tower, the process of oxidation is taking place with the help of catalyst, that is iron oxide promoted with chromium oxide and cerium oxide. So the reaction which is taking place is the carbon monoxide is treated with steam, as shown here. You can see in the flow sheet also, steam is one of the input, producer gas is one of the input, and water gas is also one input. So these three inputs are mixed at a temperature of 450 degree Celsius, where carbon monoxide is oxidized to carbon dioxide and hydrogen gas is released, you can see here. And apart from this, 410.2 kilojoule of energy is released. So the reaction is exothermic, and due to which a lot of heat is produced. So what happens here, the reaction can continue even at low temperature, means here just at the beginning, for the initiation of reaction you have to maintain the temperature. After that, the heat which is released here, 410 0.2 kilojoule energy, that itself helps to maintain the reaction temperature. So here it is, you can say, optimum use of energy. And so in oxidation tower, these gases are oxidized. Okay. The gaseous mixture of so in this oxidation tower, what are the output? The It is a gaseous mixture of carbon dioxide, hydrogen, nitrogen, and uh, some part of carbon monoxide, which is unreacted. So here what happens, these mixture of all the four gas is further sent for cooling. Okay. And heat exchanger, where heat is absorbed, and then it is compressed at 25 atmosphere. Means after oxidation tower, the energy is absorbed by heat exchanger, and then it is compressed at 25 atmosphere. And the unwanted gases, that is here carbon dioxide and carbon monoxide, are the unwanted gases here. And for the reaction we want hydrogen and nitrogen, both are desired product. But what to do with this carbon dioxide and carbon monoxide? So these gases are passed through scrubber, you can see here. After compressing at 25 atmosphere, they are sent to scrubber. Now the name itself, you know what is scrubber. Scrubber, you must have heard this name in market. The scrubbers are used to remove the unwanted thing wherever it is required. So here in scrubber, actually what happens, the carbon dioxide is removed by dissolving it in water at under pressure. So in react scrubber, what happens, carbon dioxide is dissolved in water to form carbonic acid, and this carbonic acid is removed further, and the solution, this carbonic acid is further treated with cuprous formate. Okay. And therefore this cuprous formate boiled with gaseous mixture to remove carbon monoxide and recycled. Okay. So this carbon monoxide, as you know, it again sent to at the beginning to produce water gas and producer gas. Okay. So here it is scrubbed and it is purified. Okay. So these two are the important steps where carbon monoxide and carbon dioxide is purified. Now after purifying, what is left? Nitrogen and hydrogen. So here further it is sent to converter. So here in converter, what happens, first it has to be compressed at 200 to 300 atmosphere. Means these both the reactants are in the ratio of 1:3, is further compressed to 200 and to 300 atmosphere. So in that compressor, once these gases are compressed, they are further sent to oil filter. So if there is see this carbon monoxide, as I told you in the last lecture, that it is prepared from some hydrocarbon or other sources. These are the sources of carbon. So in this hydrocarbon, there are chances of presence of some oil. So what happens, this oil is removed in oil filters. You can see here, after compressor, the gases are passed through oil filter. After oil filter, the mixture, that is mixture of nitrogen and hydrogen, is passed over finely divided iron catalyst. Actually it is sent to ammonia converter, you can see here. So in this ammonia converter, what is there? There is a finely divided iron catalyst with molybdenum as promoter. Means here on the surface of molybdenum, iron catalyst is there. So they help each other to enhance the catalytic activity. And this reaction converter is kept at 500 degrees Celsius. And this Converter is a vessel or big container where ammonia gas is produced. So this container is made up of special steel of nickel, vanadium, chromium steel. Okay, normally the steel which we see, steel material or steel utensils you see at home, they are made up of steel, chromium and carbon. Now this is nickel, vanadium, chromium steel that is used for this conversion. The catalyst in the granule form is kept at the central position of the converter. Means the reactant, as you know, is a gas. So they to means these gases should become in contact with the catalyst. So this catalyst in the granular form is kept at the center of the vessel, so that as soon as the gas is passed in this converter at high pressure, that is 200 to 300 atmosphere, they will come in contact with this catalyst. So here this is the reason why the output is 19%. Why not it is more than 50% or large? The reason is reactants are gaseous, catalyst is solid, and so on the surface of the catalyst this reaction is going to take place. So it becomes very difficult to come in contact all the three components of the reaction, that is nitrogen, hydrogen and the catalyst. So as far as possible under pressure it is tried to come bring them in contact, so the output is, or you can say yield is low, and the catalyst is present in the granular form. As I told you, the gases are heated at 500 degrees Celsius, so the reaction temperature is fine and passed through the catalyst. So here in the reaction converter, the reaction takes place like this. So the nitrogen 1 volume and the hydrogen 3 volume, means 3. See, actually why they are taking in volume ratio, again while discussing physico-chemical principles we'll discuss in detail. Here I will tell you the when you go for weighing of solid material, you take it in gram. Okay, so whatever is the molecular weight, if you take that much gram of that substance, you will get 1 mole of substance, that is Avogadro number of particle. But the same case if you go for gases, for gases it is volume, that is as at 22.4 liter at NTP, 22.4 liters of any gas contains 1 mole of substance. Okay, now here you want 3 moles because you require 3 hydrogen atoms and 1 nitrogen atom. So it is taken as 1:3 proportion at 500 degrees Celsius. It is converted to ammonia in 2 volume. Means here look at that, volume is reduced and lot of energy is released. The reaction is exothermic. Okay, and it can continue even at lower temperature. The required temperature is maintained by adjusting speed of entering gas. Okay, so required temperature is maintained here means every time whenever conversion is taking place, energy is released. So how much temperature has to maintain, it depends on how much conversion should be there, and depending on that the gas the speed of gas entering in the vessel is maintained, so the reaction can be continued at lower temperature. So you can see here the gas ammonia in ammonia converter, all these changes are taking place. The outgoing mixture contains 8% of ammonia, or mostly up to 19%, you can say. So unconverted nitrogen and hydrogen, so what to do with that? The mixture is cooled first by circulating cold water and then by ammonia refrigeration. Means here it is, you can see after ammonia converted they are sent to water chiller. First they are chilled by water converter, water chiller. So a lot of energy is absorbed, and then ammonia refrigeration at minus 15 degrees Celsius. So the reaction is sorry, the products are cooled so that liquid ammonia is formed at the storage tank, okay, and then mixed with fresh compressed gas mixture in the compressor and recirculated, okay. So when the gases are cooled, the liquid, you can see here, see the separator, then it is sent to ammonia refrigerator. After ammonia refrigeration, liquid ammonia is formed, while nitrogen and hydrogen gases are not liquefied. Only ammonia is liquefied, and it is sent to storage tank, whereas the other gases, that is nitrogen and hydrogen, they are sent to centrifugal circulator, and they are again sent to compressor and recirculated for the process. So in this way, ammonia is manufactured by Bosch Haber process, that is called as modified Bosch Haber process, okay. So the now we'll see the physico chemical principle behind the manufacture of ammonia. Means, what is physico chemical, what is the effect of temperature, what is the effect of pressure, what is the effect of catalyst, all these things are discussed so that one can understand the process clearly. So physicochemical principles, first we should know this reaction. In the last slide also same reaction we have discussed, that is nitrogen and hydrogen, they are taken in 1:3 ratio of volume, and you get product as 2 volume. What do you observe just by looking at this reaction? The first thing, the reactant, you can see here, the reactant is here 4 volume total, okay. So but the product is 2 volume, means you can see here volume is reduced, okay. When volume is reduced, pressure is increased, okay. So it is a Boyle's law, that is pressure and volume, they are inversely proportional. So compared to reactant, as the process proceeds, that is the reactant is converted to product, the volume get shrink, so pressure increased, and here you can see energy is released, okay. So the energy this is exothermic reaction. So obviously the temp, as the reaction will proceed, the temperature of the reaction will go on increasing, okay. So this, and you can see here clearly at the center, the reaction is reversible. The forward reaction is exothermic, backward reaction is endothermic. During the formation of ammonia, there is a decrease in volume, as I told you. So according to Lee Catelier's principle, percentage of ammonia formation, means here this is a reversible reaction. So if you want to shift the equilibrium to the product side, that is if you want this reaction to go in the forward direction, means forward reaction should be dominating. If you want, then the equilibrium will increase with increase in pressure and decrease in temperature. Means why? Because here volume is shrinking, means pressure has to increase. If you want, means forward direction, increase in pressure will favor the forward reaction. Second thing, the energy is released as a product, means this is exothermic reaction. If in this process, by any means, if you absorb, if you remove that energy, then forward reaction will be favored. So these two factors are going to play the role while deciding the actual manufacture. The equilibrium constant, now this is reversible reaction, so the equilibrium constant Kp is given as this. Kp is equal to pressure square of ammonia divided by pressure of nitrogen and pressure of hydrogen. Now you can see here, for gases we do not use concentration term. Normally for reversible reaction in solution, we write it all the chemicals in square bracket, means the concentrations are in moles per liter. But if it is a gas, you have to mention in the terms of pressure, okay. As the increase in pressure shift the equilibrium towards right and favors the formation of ammonia, the reasonable percentage of ammonia is found to be present in equilibrium mixture. Okay, so first we'll see what is the effect of temperature. If we increase the temperature, we find the system tries to decrease it. Are you getting? Means here similarly, means here when you increase the temperature, the system tries to decrease it, means it tries to absorb it. Similarly, if we decrease the temperature, the system tries to increase it. The formation of ammonia is exothermic reaction, so it is favored by low temperature. Means how? Means the reaction is increasing the temperature, but if we absorb the temperature, so at low temperature the reaction is favored. So in the table you can see here that as the temperature is increasing, okay, so here uh, shows that temperature is in, as the temperature increases, that is from 350 to 400, look at what happens to the percentage of ammonia. It decreases. So as it reaches to 450, 500, 550, slowly you can see the percent yield at 200 atmosphere goes on decreasing. Why it is happening? The reason is in the reaction itself, for each molecule 92 kilojoule is formed, or you can say released. Now if you are still supplying heat from outside also, obviously what happens, the reversible reaction will favor. Okay, so therefore increase in temperature will decrease the yield, whereas in decreasing temperature will increase the yield, and that goes up to 37.5% also. So the equilibrium constant remains constant at a given temperature. It increases with increasing temperature and decrease with decreasing temperature. So table itself is self-explanatory. So from this it is very clear that at lower temperature the yield is high, but at lower temperature the rate of reaction is slow. Means as the temperature decreases, rate of reaction decreases. Therefore the converter, in the converter optimum temperature is kept and the rate of reaction is increased by using catalyst. So with the decreasing temperature, rate is going to decrease, but its rate is increased by use of catalyst. So even at the lower temperature the yield goes on increasing. So now you have understood why it is necessary to understand the physico-chemical principle. If you know this chemical physico-chemical principle, you can investigate and you can innovatively decide how you can maintain the favorable conditions. So use of catalyst is to decrease the temperature, which is a favorable for forward direction. Now second factor is effect of pressure. In the above reaction, means this manufacture of ammonia, this reaction, you can see that reactant side there are 4 times volume, whereas in product side there is a 2 times volume. Means as a product the volume of reaction in the product goes on decreasing. So with decrease in volume, what is going to happen? Pressure is going to increase. So forward reaction is favored by increase in pressure. The equilibrium will shift in such a direction that number of moles and hence the volume decreases. If we increase the pressure, we find that more amount of ammonia is formed. In general, the reaction which is accompanied by the decrease in volume is favored by increase in pressure. So here you can see the figure. Okay, at different pressures, look at the graph. So you can see mostly 0 to 200, you can say the pressure as you go on increasing, what happens, the output also goes on increasing. At 200 degrees Celsius and pressure 750, at 200 degrees Celsius and 750 atmosphere, the reaction is almost 100%. Look at here. Okay, You can see here, initially increase in pressure for all the temperature, it rises exponentially, then it increases steadily. But at as the pressure goes on increasing, look at here, at 750, means initially you go on increasing the pressure, 0 to say 100 exponential, after 100 linear, and when it reaches to 750 here, somewhere here, it goes to highest point. Okay, that is almost 100%. Okay, since there is a difficulty associated with taking large amount of material at this high pressure, the lower pressure of around 200 atmosphere is used industrially. Means see, look at here all the graph at different way. Generally at 200 atmosphere pressure, the output increases exponentially, after that it increases linearly. So this exponential benefit is taken care by maintaining 200 atmosphere. So by using the pressure at 200 atmosphere and temperature at 500 degrees Celsius, the yield of ammonia is 10 to 20%. Again I am mentioning here that you will say why pressure is not maintained at 750 atmosphere and 200, because again, though theoretically we can reach to 100% output, but here the maintaining that pressure at these are the gaseous reactants, so it will be you can say uh, uh, it will be unsafe, it will be threatening to maintain the reaction at such a high temperature. So the optimum conditions are 200 atmosphere and 500 degree Celsius. So by looking at this, you can say here, so just look at the pressure, as the if you maintain the temperature constant, say 400 degrees Celsius, what will happen? Look at the temperature is 400 degrees Celsius. As the pressure increases, the yield increases. So here lower temperature and higher pressure will favor the reaction output, that is yield. Now here for today we'll stop here. Next time we'll discuss the effect of catalyst and uses of ammonia, and that will complete our first basic chemical, that is ammonia. Now here I will conclude for today's lecture. We'll meet in the next lecture. Thank you.